So, welcome everyone. TCS seminar at the Agilanian University. Today we have a pleasure to have Sangil with us. Sangil, PhD in Princeton in mathematics or in computer science, actually. Applied math, okay. After that, positions in many places. Where was it? Waterloo, Georgia Tech. And finally, since I remember, a professor first at KAIST, and as I learned now just at IBS, which is a Korean research institute of basic sciences. Sangil is a leader of a group there. It's great to have you here. Please show us some of the latest research.
Thank you. Thanks for coming. Thank you for inviting me. It's my first time to visit Krakow. Very nice so far. I want to visit again. Yeah. And I tried to choose a subtopic that some of people didn't see, because last week I gave a talk and there were many people from this group who saw the talk. So I chose different topic. So this is about a fun project with Bruce Reed and with people in my group about the treewidth of graph. So Bruce Reed was a professor at McGill in Canada, but 2 years ago, he moved to Taiwan. Then I thought, maybe it's good to invite him to Korea. We are very close. Flight was very cheap, so I invited him, and we spent some good time, and then had an interesting collaboration. And Pascal Borin was a former member of IDS. Now he's in Moscow, and Kevin was also a former member. Now he's in Australia. So maybe for this audience, probably, I don't know. So I studied the definition of minor. The minor of graph is any small graph obtained from the bigger graph by a sequence of deletion and contractions. And you can delete edges, contract edges, or you can delete vertices. So the many important concepts can be characterized in terms of the minors. So for instance, Grotowski-Wagner's theorem says planar graphs can be characterized by forbidding two particular graphs. And more generally, any graph class closer to taking minor is characterized by a finite set of forbidden minors. And by the way, how long is the talk?
60 to 90, whatever in between is okay.
I see. Probably I don't need that much hours. So.
It's okay.
Yeah. So one of the theorem in graph minors is the well-quasi ordering, so that any finite set of any class of proper class of minor class is characterized by a finite list of forbidden minors, and equivalently, another way of stating the same thing is to say that any infinite sequence of graphs must admit a pair such that the ith graph in the sequence is minor of the jth graph. And this is a well-known theorem of Robertson-Seymour. And when they proved this well-quasi ordering, there were several sub-cases, and one of the easier case is when the first graph is planar. If the first graph is planar, then we can assume that none of the other graphs contains the first graph as minor. So we can assume that G2, G3, G4, they don't have a minor, G1 as minor. So if you forbid fixed planar graph as a minor, then interestingly, Robertson and Seymour came up with the structure theorem. So any graph doesn't have a fixed planar graph minor, have something called bounded treewidth. So treewidth is bounded by a function of the this fixed forbidden graph. And then they have a separate paper showing that graphs having this kind of structure is well quasi-ordered. Right? So that's part of the their strategy. So depending on the first graph you forbid in the sequence, then the other graphs have certain structure, and then they prove that these graphs with that structures are well co-ordered. So this talk is about this theorem about forbidding planar graph, and then you have this bound on treewidth. So any planar graph is minor of k by k grid. So you think of the numbers, right? So what is the bound? How big is the tree width in order to contain k by k grid? And the initial theorem of Robertson-Seymour, this number is huge. So we don't even want to write down the number. But then later, they have improvement, the bound to get the k by k grid minor. Tree width is bigger than or equal to 20 to the 2k to the 5. No, actually, yeah, so that number. So if it's bigger than the number, then tree width, then you have a k by k grid minor. And this has been improved step by step. So in 1999, Diestel and others improved it. So the exponent is slightly better. No, maybe I missed. Oh yeah, no. The base of the exponential function is better. Instead of 20, now it's 2.
So this is not it's the same as k by k.
Maybe I copied the wrong number. But anyway, and then around 2012, there were 2 independent papers. Kenichi Kobayashi and Kobayashi had something like 2 to the k squared log k. I mean, both of them. So Leaf was undergraduate student of Paul Seymour, but they also came up with 2 to the k squared log k. Yeah.
K denotes the treewidth something?
Oh no, the k is the k by k grid.
Grid.
Yeah, so you want to get the k by k grid as a minor. So the question is, how big is the tree width? So these 2 are comparable numbers. And I remember hearing that Paul Seymour was editor of some journal where this paper was submitted. So it was sitting in his email box. He didn't know. So, but has a paper independently, and then later realized that they have a similar theorem. And first polynomial bound was found by Chuzhou and Tan. So that was in 2021. So now we know that this f can be taken as a polynomial. So if tree width is bigger than constant times k to the 9 times log k, then you contain k by k grid minor. So let's say this function f of h to be the function, right? So if tree width, so if the graph doesn't have h minor, then tree width is at most f of h. And then we can think of the best possible function for this tree width bound.
So it's defined only for planar graphs, right?
Yeah, right. So if it's non-planar, this number is not defined because planar graphs have arbitrarily large tree width. So therefore, and they don't contain non-planar graph as a minor. So if h is non-planar, then f of h is infinite, right? And then I have this blank slide. What is tree width? For this audience, I don't know, but I will skip. I will skip up. I will give you alternative definitions. So one way to see the h minor in a graph G is instead of using deletion contractions, you can think of it as a collection of disjoint vertex sets. So each vertex set, so I have x1, x2, xt. These are the disjoint vertex sets. Each of them induces connected subgraph so that you can later contract. And then whenever there's an edge between vi and vj in H, then I want to have an edge between xi and xj. So that when you contract xi, when you contract xj, you have a one edge remaining. Okay? So some people prefer writing this as a minor. Right? So this, when you say a graph G has H minor, you contain this kind of collection of disjoint vertex sets. And then there's the easy fact that when you have H minor, then treewidth of H is less than or equal to treewidth of G. Okay, I didn't explain the definition of treewidth, but then this is its fact. And if H is a complete graph, so KT, then everything is same, but in KT, every pair of vertices are adjacent. So for any distinct ij, xi and xj, there's an edge. Okay? So that's KT minor. And KT has treewidth T minus 1. So obviously, if you have a KT minor, then treewidth is at least T minus 1. So that's a lower bound, right? So if you have a KT minor, treewidth is big. And we can slightly modify this further, so-called bramble. So now I don't say that xi's are disjoint sets. It's a collection of vertex sets, each of them inducing connected subgraph. But for any pair ij, now they might intersect, right? So either they intersect, or if they don't intersect, there's an edge between them. So we say, in that case, some people say they touch, xi and xj touch. And then, this nice fact that if you have a bramble of order k, I will just explain what the order of the bramble is, but there's a fact that if you have a bramble of order k, then treewidth is at least k minus 1. So in particular, the clique minor, complete graph minor is a bramble. When you have a KT minor, then that's bramble, because pairwise they touch, and each induces connected subgraph. So this is generalization of the previous slide. And order of the bramble is minimum size of hitting set for the bramble. So I want to have a collection of vertices so that every bramble element, every xi intersect with this set. So among all possible such a hitting set, I want to find the minimum size set. That's the order of bramble. And Seymour and Thomas proved that this is actually equal. So treewidth is equal to the minimum order of bramble plus 1. So this is the definition that I'm going to use. So the treewidth, if treewidth is big, then there's a bramble. And now, since Chuzoi and Tan have this paper saying that f of h can be taken as polynomial in the size of h, we may wonder whether f of h could be improved to a linear function, but actually not, because Robertson, Seymour, and Thomas remarked in their paper that when you have G by G grid, f value of that graph is at least G squared times log G. So G by G grid has G squared many vertices. So this is like number of vertices. So if you have n vertices, then it's n log n. So there are certain graphs where the treewidth, linear treewidth, doesn't force to contain that graph as a minor. And the proof was by constructing certain graph by probabilistic method, getting some small graph with large treewidth, with large girths, so that if you have a large grid minor, then you will have many cycles, but girth is big, so there's an issue. So when do we have this function linear? So there are some known cases. So if h is, for instance, forest, and we knew from a paper in 90s. So let's say h has n vertices, and it has to be planar, right? So if h is forest with n vertices, we knew that f of h is exactly n minus 2. And it cannot be n minus 3 because kn minus 3, no, kn minus 2 has treewidth n minus 3 and doesn't contain n vertex forest as a minor. Yeah, maybe. Yeah. So did I say wrong? Okay, that's forest. And then it is generalized to cycles, like Fellows and Langston has a paper which proves a small lemma saying that if you have a treewidth, if you don't contain cycle, then treewidth is at most n-2, the same bound. And then k to t, you have 2n-6, still linear function of n. If you have the apex forest, so this is the graph where if you delete one vertex, remaining is a forest. Then initially in 2019, same Leaf and Porsimer has a paper proving that it's at most 1.5n. And Chunung Ru and Yongho Yu improved it to n-2. And then there were some known conditions. So by these author paper, they show that if this is linear, then you cannot have too many vertex-disjoint cycles in the graph H. Now, so one of the first theorem I want to say is that the converse, we didn't prove the converse, but we proved the converse when H is very simple type. So when H is disjoint union of trees and planar graphs of small number of vertices, then the converse is true. And here, the number of, so this bound R is fixed. So if every component has a small size or is a tree, then we know that this is true. That's the first theorem. And the second one is about the disjoint union of cycles. So we prove that if H is disjoint union of cycles, and if you have R cycles, then you have the f of H less than or equal to 3/2 times n plus CR squared log R. And if I have time, I can show you the proof. And when you have only 2 disjoint cycles, we can do slightly better. Instead of 1/2, 3/2 n, we can have n. And third one is what happens if you have a subdivision of small planar graph, and then we can get something like r times n, where r is the number of edges of the initial planar graph. So we try to collect all kinds of small examples. And this is a different, slightly different thing. So we were wondering about 4x4 grid. How big is this number? So how big is it necessary to have treewidth so that you always contain 4x4 grid? So previously, I don't know how to pronounce his name. So anyway, Bondi and Bruce Reed, and they proved that f of 4x4 grid is at most 7,262. And then we spent some time, and then 160 is enough.
Why 4x4?
Yeah, we can do other numbers, but 4x4. Okay, there's some nice toy lemmas that you will see. So 4x4 grid is like this, right? Now, the structure that I'm gonna show you is this twisted L prism that consists of 2 cycles of length L joined by a matching. And the reason why I say twisted is because this ordering of the matching can connect these vertices in arbitrary order. So if I don't have twisted, just L prism, then the first vertex is mapped to first vertex of the second cycle, etc. Then it's L prism. So 4x4 grid is nice. The reason why we work with 4x4 grid, and also they work with 4x4 grid, is because when you have a big twisted prism, then you can, here you have 2 cycles, right? 4x4 grid has 2 disjoint cycles with many edges between them. So if you have a good twisted L prism for some L, then you can contract to get a 4x4 grid minor. So that's the, yeah, you cannot use same approach for 5x5 grid minor. So to improve this number, we came up with several steps. So the first one is, like, if you have a, so if you graph G has no twisted L prism minor for any possible connection between two cycles, then treewidth is at most that bounds, twice L plus something. And second one is, like, you don't have L prism, and also you don't have a K vertex wheel minor. So the wheel is a cycle plus one vertex adjacent to everything. Then we have a similar thing. And then third one is, if you don't have 4x4 grid minor and no twisted L prism, you have 12 plus 10. So this kind of thing is used to prove that Apple 4x4 grid is at most 160. And this work was a lot of fun because probably nobody cared whether it's 160 or 161. But it's like, yeah, I can show you like really fun part, some engineering part, how to shape off like 1 and 2 from the existing idea. Right. So for instance, here is a step. Right? So I want to say that twisted 75 prism has 4x4 grid minor. Okay, so you have two cycles joined by 75 edges. Then I want to say that there is a 4x4 grid minor. So how do we do that? So there are two cases. The first case is that you have a quadrangle, C4, somewhere. Like two edges of the matching together with the two edges in the cycle. If you have a C4, what can you do? Then I'm gonna number the vertices of the cycle in a cyclic order, starting from here, right? The one end of the one rectangle, the square, and then you number these inner cycle and outer cycle. But I just have numbers for inner cycle, and then on the outer cycle, I have corresponding numbers based on matching. Then these numbers on the outer cycle give you a sequence, right? So a sequence of integers between from 1 to 75, but 1 and 75 are at the end. In the middle, it's permuted, right? It's a permutation of numbers from 2 to 74. So there are 73 distinct integers. And the reason why I chose 73 is it's 8 times 9 plus 1. So the Ellis-Zacharias theorem says that when you have a sequence of length 8 times 9 plus 1, then you either have increasing sequence of length 9 or decreasing sequence of length 10. So that's weird. So if you have an increasing sequence of length 9, then we get this nice prism. If you have a decreasing sequence of length 10, then just ignore one and then flip the other. So, right, so think of delete one of the edges and then rotate this cycle. And then you get a 10 edges from inside to outside in the correct order. So in both cases, we got the prism. I mean, it's 10 prism. Right? No, 10, 9, 10, 11 prism. So 11 prism, we got 11 prism. But initially, the length of the cycle was long. And when you look at the 4x4 grid, I need to have at least one. So if you have a 10 of these edges, so 11 of these edges, I can contract the inner cycle. and make sure that one of the vertices at the corner is one of the vertices that is not instrumented matching. So that's what I need, right? So that's 11. So by contraction from that 11 prism, I got 4x4 grid. So 75 prism is good for us. But what if you don't have a quadrangle? What if you don't have a C4? Now, it's 75, twisted 75 prism, and 75 is bigger than a squared. So I can find the increasing or decreasing subsequence of length 9. Right? But if it's a reversed order, I can switch the ordering. So I can arrange picture like this. Now the trouble is that I want to construct the inner cycle so that degree 2 vertices are located here. That's the trouble, right? Because I might have a situation where after contraction, maybe one of these edges missing, then that's the trouble. So one good case is when you have a 1 degree 2 vertex in between X and Y, and another degree 2 vertex between Z and W, and they are distance 2 between them. So X, Y, Z, W are 4 consecutive vertices on the outer cycle having matching, so that there's some subdivisions, there's some subdivision here. In this case, I can contract here, make sure that this is one of the corner vertex, this red vertex is the other corner vertex, then you get the 4x4 grid minor. So that's good case, right? If you have such a thing, you get a 4x4 grid minor. So let's assume that we don't have such a thing, right? So that means now I had 10 segments, right? So 9. And most 4 edges of the outer cycle is subdivided, because if one of them is subdivided, then this is not subdivided, right? So I can just do pairing. So one of them is not subdivided, one of them is not subdivided. So at most 4 of outside is subdivided, and similarly, at most 4 of inside is subdivided. But there were more than 8 edges of the cycle. So one part, so there's a pair of the edges, both are not subdivided, and there's a C4. So that's so this is contradiction, because we assume that there's no C4. So this is like how you get the 4x4 grid minor if you have a twisted 75 prism. And now, then we prove that if you have a no twisted L prism and 4x4 grid minor, then twisted at most 12 plus 10, where I think you will just put L to be 75, right? And then you get a bound times 75 plus 10. So how do we prove such a thing? So suppose treewidth is bigger than 12 plus 10, then there's a bramble of order something. Now, there's a nice lemma that if you have a bramble of large order, then I can find the cycle hitting every bramble element. So how do I prove that? Well, take the shortest path hitting every bramble element. So let's say this x1, x2, x3 of the xn is shortest path hitting every element in the bramble, fix the bramble. Now look at the first vertex. This is shortest path, so if I delete x1, it's no longer has hitting set. So that means there's one bramble element that is only intersected by x1. Same for the last vertex, right? There is a one bramble element only intersected by xn. Now, this is connected subgraph. That's connected subgraph, and they touch each other. So either there's an edge or they intersect. So that means from x1, I have a path to some place which is joined to a vertex here, and then there's a path. And these vertices are disjoint from the vertices here. So there is a cycle. So whenever you have a large bramble, the bramble of large order, I have a cycle intersecting every element in the bramble. So that's the proof. And another lemma is that when you have a so let's say you have a fixed bramble B, and I have two sets S and T, and I look at all elements of the bramble intersecting S and all elements of bramble intersecting T. If both of them have large order, right? So BS is the bramble intersecting S side. T is the collection of the bramble elements intersecting T side. If both BS, BT have large order, then I can find many disjoint paths from S to T. Why? Because if I don't have many disjoint paths, by Manger's theorem, there's a separation. Right? There's a small number of vertices hitting every path, so that's separating S from T. So if this is this is not a hitting set for bramble on S because this size is too small. The order of bramble is bigger than or equal to L. This set has length size less than L, so it's not a hitting set. Order is smallest the size of hitting set. So this is not a hitting set. That means there's a bramble elements disjoint from X, but intersecting S. Similarly,
I found this on the
there's a bramble elements intersecting T, not intersecting X. Now, these two, X and Y, are from initial bramble. So therefore, they pairwise touch. So there should be an edge between them or they should intersect. But that's not possible. Right? After deleting X, there's no edge from left-hand side to right-hand side. So that's the contradiction. That means you have many L disjoint paths from S to T. So these are the tools. Right, so now I can show you the idea of the proof. So by lemma, since treewidth is big, there's a bramble of large order, so there's a cycle intersecting every bramble element, and the cycle has to have a length at least 12 plus 12 because the cycle itself is a hitting set. So bramble has large order, so it cannot be too small. Now I have this cycle, and then pick one vertex and take the subpath of the cycle so that collection of elements of the bramble intersecting this subpath has order at least L. And I want to choose the minimal such path, the shortest path from S1 to T1 so that the minimal subpath of the cycle so that the collection of sub-bramble elements, collection of sub-bramble intersecting this path has order at least L. So that's one side. I do the same thing on the other side. Pick one vertex. So S1, T1 are slight, S1, S2 are slightly far, and then from here, I try to find the subpath so that it intersects a bramble of order at least L.
Besides cycle.
Oh, what is the case?
You have a cycle.
Yeah.
It's long, yeah?
Yeah.
And then you say, so one side of the cycle.
Yeah. So, no, I don't split half, right? I just pick one vertex and take a one path, and then I choose another vertex, maybe distance 2 from S1 or something. So
okay, but then how do you know that the second path is disjoint?
Right. So you're worried about, well, what if this goes too long and they intersect, right?
Yeah, sure.
So length of this cycle will not be right. So yeah. So initially, so I chose the S1. So when I choose T1, it's a minimal one intersecting this. So that means when I delete the last vertex, the sub-bramble has order less than L. So that means it's order exactly L.
Well, I mean, this last vertex could hit a lot.
Oh, no, the order of the bramble is the minimum size of hitting set, right? So if S1 to one vertex before has order strictly less than L, then I can hit everything by just hitting, by using the previous hitting set plus one more vertex, T1.
You can hit L bramble.
Yeah, order exactly L bramble. Right?
Why this last vertex important? Yes, order L.
Yeah.
Many elements, but order L. Yes.
Oh yeah, order is L. Right? So you might have many sub-bramble
Yes,
bramble elements, but order is exactly L. So if I ignore all the sub-bramble elements intersecting first pass, the remaining has order still L plus some constant. And then if I take this, it cannot cover everything. It will also stop when the order of the bramble is exactly L. So I had this slack, right? 2L plus 11, so I have some spare room. Yeah, so that's how we got these two things. And now, this is the imaginary situation. So what if I have pass from S to T1, S1 to T1, and another pass from S2 to T2, disjoint from this thing, so that I have two cycles. And then, since there's a bramble of order at least L here, bramble of order at least L there will be L disjoint path. Then that gives me a twisted L prism. So, right, so if there's a S1 T1 pass, S2 T2 pass disjoint, then this L disjoint pass is coming from previous lemma. So we get twisted L prism. So we can assume that we don't have this disjoint S1 T1, S2 T2 pass. And then there's a T2 pass theorem. Then if you have a graph where you don't have a vertex disjoint S1 T1, and yeah.
Two yellow cycles, can you assume that they are different? With these sub-brambles?
Oh yeah, I mean, I'm saying that if they are disjoint S1, yeah. There could be intersecting one, but if there's a disjoint one, then I'm happy. And the theorem is that if you don't have disjoint such paths, then you have a structure. So this two-path theorem says that if you don't have such disjoint path, then your graph is pretty much like a planar graph with some embedding like this, where outside you don't have anything, you have a cycle, S1, S2, T1, no, not a cycle, but it's embedded in this way, that S1, S2, T1, T2 are on the boundary, and everything else is inside. It's planar, except you might have small separations, something like 3-vertex cut separating some component. This 3-vertex cut is necessary because when you have a 3-vertex separation, then they don't help us. So if this part is planar, then topologically you don't have a disjoint path. S1, T1, S2, T2 will always intersect. And if you have a 3-vertex cut, you cannot also intersect, right? Even if you go in, so these paths can only use, I mean, if one path goes in and out, the other path goes in and out, then they must intersect. And this is the structure theorem. So using that, we can use that. So since we can assume that there's no S1, T1, S2, T2 disjoint paths, therefore the graph is like planar, except these 3 separations. But for 3 separation, I can contract outside to make a triangle.
But something I don't understand. So the structure theorem was about crossing paths.
Yeah, S1, T1, S2, T2.
Okay. Yeah. And on your slide with your big picture, this is.
Oh, so this is independent of embedding. There's like S1, T1, S2, T2, whenever you have any two S1, T1, S2, T2, then graph looks like this. Graph can be embedded on the plane like this way. So,
But don't you have to assume that they are in the clockwise order around the cycle? Whatever is embedding on the
so
cycle.
the theorem actually gives you this kind of ordering. So I don't have to fix any embedding. It's about theorem for any graph. So that means I can contract these components outside of three separations. Then I get a planar minor. So the whole graph will have a planar minor structure. And then remember, these green parts still have bramble of order at least 14, because I cut out these brambles over the L, over the L. So initially I start with the 12 plus something. So I still have a leftover bramble elements, which still make a large order. So I have a minor and still have a bramble of order 14. So treewidth is at least 13. Then now I am ready to cheat because I can use the theorem. So there's a theorem by Gu and Tamaki that they prove that if treewidth is 9/2 times G minus 5, then you have a G by G grid minor. So, okay, now let's use it. Let's say G is 4, then treewidth 13 implies 4 by 4 grid minor. So in one case, we use many decision paths, construct the grid from the twisted wheel. The other case, we just use this theorem. So that's how we prove the bounds. Yep.
Just explain that you don't have a planar graph, you have a click sums.
Right.
Something that you don't know.
Right. So we have this click sum, but we will contract them down here so that we make a planar. So,
okay, but when you contract it, how do you know that your bramble survives?
Right. So the bramble, yeah. So that's some part we need to prove, but it's not very hard. Yeah. Because basically bramble. So these things intersect the bramble, and for any xi, yeah, it stays outside of these separations. Right. That's what's hidden here. And the reason why this theorem has a better bound is because they assume that the graph G is planar. So when you have a planar graph with treewidth linear, then you have a G by G grid minor. And so this is how we prove 160 implies 4 by 4 grid minor in general. Now, this is the first part of the first theorem, the converse. So when you have not many vertex-disjoint cycles, then f of h is linear. This is only when h is a union of trees and small planar graphs. So what we use is this nice lemma by those 4 people. They prove that when you have a good tree width, then you can partition the graph into small number of the k parts. Each of them has a large tree width. Oh, there, this is a large R. So when you have large, for every R, there's an S, some constant S, so that if tree width is bigger than S times K log K plus 1, then I can find the vertex-disjoint induced subgraphs. Each of them have tree width bigger than R. So what we're gonna do is take the K as the number of non-tree components of H, and
There's no R in this lower bound.
yeah, so the capital R.
What?
Oh, maybe
There's no R.
yeah. So but S depends on R.
Oh, of course.
Yeah, S depends on R. It's not right. Right. And let's take the R to be the maximum f of G for all planar graphs on most small r vertices. So whenever treewidth is bigger than r, I contain one of the small planar graph. That's my bound, capital R. And then if I use this lemma, then if H prime is disjoint union of all non-tree components of H, then if H prime is less than that bound given by this lemma. Because if you have a graph of treewidth bigger than that, then you have a disjoint union of this. You have K graphs, each of them have treewidth bigger than R, and each of them contain one of the planar graph in H. Now, how do we take care of the tree components? This is the easy part of the thing. So let's say H is disjoint union of H prime and a tree T. Then we're gonna prove that f of H is at most f of H prime plus size of the tree. And this is coming from this proof that graph of large treewidth contain graph of large pathways contains a tree as a minor. So there's a lemma saying that you can find the separation where left-hand side has path decomposition using the A intersection B as one of the back, and left-hand side has a tree minor on A intersection B. So we use that lemma. So that means we can construct T from A side, but the B side will have a still large treewidth. Even after deleting A, we will have large treewidth because if you have 3D decomposition of B side, I can attach the path decomposition on one of the back having intersections. So this is why f of H is number of vertices of tree plus the others, so it's still linear. All right, there's some other things. Like if you have a disjoint union of cycles, what do we do? Here we use the Eldridge-Fossat theorem. If you have either you have many disjoint cycles or you have a small set hitting every cycle in the graph. So we're gonna prove that if you have a no H binary, then treewidth is at most 1.5 n plus this sum of C, K, log K. K is the sum, right? So the one of R, sorry.
R is the number of cycles in H.
No, R is number of cycles. So so sum will be C, K square, so C, R square log R. Yeah. And now let's assume that I have a graph of treewidth large and fix one bramble of large order. And then there's a cycle hitting every bramble elements. I start with the subpath intersecting bramble of order exactly C1 minus 2. C1 is the length of the longest cycle in H. And then I take another bramble of order twice CR log R and another subpath intersecting bramble of order twice CR log R. Now, I have these two paths, P0 and P2. So P0, P1, P2. If I have many paths between them, then I have many, I know already there are many paths between them because each of them has large order. So remember we had a lemma that by using Menger, there's many paths between P0 and P2. So first case is when each of them has length long. If each of them is long, then just look at the subgraph made by these edges of P0 and P2 and the edges of the path. Now, we use Eldridge-Fossat to find the are disjoint cycles here, because Erdős-Pósa says either you have R disjoint cycle or you can delete small number of vertices to fit every cycle. So if you delete small number of vertices to hit every cycle, that's impossible here. So basically you will no. Yeah, so you will find many disjoint cycle and each of them is long.
Why is it impossible?
Maybe I can miss.
What is the size of the set that you remove?
Right, size of set I remove is like CR log R, right? That's why we chose this thing. Yeah, so if it's a CR log R, and then the treewidth was big, so if I delete,
There's more buffs than
yeah,
buffs survive.
yeah, so maybe I should, yeah, so I should contain this bramble, and then path consideration. Yeah, so this was true. This has a order twice CR log R, so even if I delete R log R and still have a large treewidth.
Okay, so then you have cycles, but each cycle has to contain this long. So each cycle is long.
Yeah.
So this means that you have H as a minor.
Right. Yeah. Each cycle is longer than C1, so.
Yes.
And then case 2 is maybe one of the paths is short. Then what we do is we're gonna use this path together with P1 and some part of P0 and part of P2. And then the length of that is not too much. So this hits a bramble of order C1 minus 2, and then there's a short path, and then this hits some bramble, but this part already hits bramble of order big. So here you have a cycle of length and list C1 because P1 was long. P1 was long, so this is long length and list C1. And here, there used to be bramble of order something. So even if I delete this cycle, I still have large order bramble. So treewidth is big. By induction, I get the remaining cycles. Yeah. So this is the proof.
So you pay for the cycle that you find, you pay order K log K because of P0 P2.
Yeah, that's right.
And then you
keep, yeah.
So that's why when you have R cycle, you have the sum.
Right. Now, recently, Michael Hatzel and Chunung, Bruce Reed, Sebastian Bidurat uploaded a paper on arXiv, which has slightly better bound. So basically, we had R squared here, but they reduce it to R.
So they multiply.
Yeah, but then they multiply length of the cycle, so log R or L, right?
No, but they also multiply the n part.
Oh yeah, that's true. Yeah, CM log. Okay, I see. Right. So, but if you only consider, I mean, if you sustain the lengths and more some linear, so if your bound is like L is linear, then maybe this is better bound, maybe. Yeah. Anyway, this is the last slide. So, one cute question I don't know. I mean, whether it's really doable optimally is, can we reduce 160? You see, there were a lot of rooms, right? I played with all these sectors and so, I mean, I don't think 160 is the correct answer. There should be something smaller. And the other question is the converse of the easy observation, right? So one direction, I showed you the converse when H is the disjoint union of the boundary size planar graph and trees. But what if you have arbitrarily large graph, then is it true? So that's the second problem. So that's it. Thank you.